Let's take a quick look at relations that you learnt in your previous class. A relation R from a non-empty set A to another non-empty set B is a subset of the Cartesian product of A and B. The subset R is derived by describing a relationship between the first element and the second element of the ordered pairs in A cross B. Let us see an example to make our concept stronger. Here, we have to find a relation R from A to B such that for any A in A and B in B, A is a factor of B and also A is less than B. That is, in the given sets A and B, we have to find the set of ordered pairs A, B such that A is a factor of B and A is less than B. Let 2 and 4 be any arbitrary elements of sets A and B, respectively. Now, 2 is a factor of 4 and also 2 is less than 4. So, 2, 4 is one such ordered pair that satisfies relation R. Likewise, other such ordered pairs can be obtained. Thus, the set of all the ordered pairs so formed is the relation R, which is as shown. The set of all the first elements of the ordered pairs in a relation R from a set A to a set B is called the domain of the relation R, and the set of all the second elements of the ordered pairs is called the range of R. If the ordered pair A, B belongs to set R, then we say that A is related to B, which is denoted by ARB. You also learned that if the number of elements in set A is P, and the number of elements in set B is Q, then the total number of elements in the Cartesian product of A and B is PQ, and the total number of possible relations from set A to set B is 2 raised to the power of PQ. Let us now learn about the different types of relations. Consider set A with elements 1, 2, 3 and 4. The Cartesian product of A with itself consists of 16 ordered pairs, as shown here. Let us define a relation R on A, defined as the set of all ordered pairs x, y, such that x plus y is equal to 15. Recall that any relation R in A is a subset of A cross A. In this case, no ordered pair satisfies the condition that the sum of their elements is 15. Hence, relation R has no ordered pairs in it. These types of relations are known as empty relations. Mathematically, a relation R in a set A is called an empty relation if no element of A is related to any element of A. That is, R is an empty set and is a subset of A cross A. Proceeding further, let us define a relation R in A as the set of ordered pairs x, y, such that x plus y is less than or equal to 8. Choose any arbitrary ordered pair from A cross A. Observe that the sum of its elements is less than or equal to 8. Here, all the ordered pairs satisfy the condition that the sum of their elements is less than or equal to 8. Hence, we get a relation R that has all the ordered pairs present in A cross A. This type of a relation is known as the universal relation or total relation. Mathematically, a relation R in a set A is called a universal relation or total relation if every element of A is related to every element of A. That is, R is equal to A cross A. An empty relation and the universal relation are sometimes called trivial relations. There are 4 different types of relations. Let's first see when a relation is said to be reflexive. Let T be the set of all triangles in a plane. Define the relation R in T by the set of ordered pairs T1, T2 such that T1 is similar to T2. If an ordered pair T1, T1 is in set R, then it implies that T1 is similar to itself, which is true, since every triangle is similar to itself. And this holds true for all the triangles in set T. Hence, we can say that every element of set R is related to itself. Such types of relations are called reflexive relations. Mathematically, a relation R in T is said to be reflexive if every element of set R is related to itself. That is, the ordered pair x, x belongs to R for every x in T. Next, let's see when a relation is said to be symmetric. Again, consider the same relation R in T defined by T1, T2 such that T1 is similar to T2. Let T1, T2 be an ordered pair in set R. Then it will imply that T1 is similar to T2. So we can also say T2 is also similar to T1. This implies the ordered pair T2, T1 is also in R. Such relations are called symmetric relations. Mathematically, a relation R in a set T is said to be symmetric if ordered pair x, y belongs to R implies that ordered pair y, x is also in R for all x and y in T. Let us take one contradictory example. Relation R in the set 1, 2, 3 is not symmetric. This is because the ordered pair 1, 3 belongs to R, but 3, 1 doesn't. Note that it is wrong to say that it is sometimes symmetric or is symmetric as far as 1 and 2 are concerned, since being symmetric is a property of the whole relation. Let us now move on to transitive relations. A relation R in T is said to be transitive if x, y and y, z belongs to R implies that ordered pair x, z also belongs to set R. Let's check the transitivity of the relation R in T, which is defined by the set of ordered pairs T1, T2 such that T1 is similar to T2. Consider the ordered pairs T1, T2 and T2, T3 in set R. By definition, T1 is similar to T2 and T2 is similar to T3. Now, T2 is similar to both T1 and T3, so this implies that T1 is similar to T3. This in turn implies that the ordered pair T1, T3 belong to set R. Hence, ordered pairs T1, T2 and T2, T3 belong to set R implies that T1, T3 is also in R. This shows that the relation R in T is transitive. Now, let's come back to relation R in set T. We observed that the relation R in T is reflexive, symmetric and transitive. Such a relation R in T is called an equivalence relation. Mathematically, a relation is said to be equivalence relation if it is reflexive, symmetric and transitive. In this module, you will learn about different types of functions. Take a look at the diagram. It shows the graphical representation of the function f1 from a to b. On representing the given function in roster form, we obtain a set with 4 ordered pairs. Observe that different elements of set A have correspondence with different elements of set B. That means the images of different elements of set A under F1 are different. We can also say that no 2 ordered pairs have the same second coordinates. Now, take a look at this diagram. In this case also, the images of the distinct elements of set A under F2 are distinct, or no 2 ordered pairs have the same second coordinate. Such types of functions are known as 1-1 functions. Let us define it mathematically now. A function f from a to b is said to be 1-1 if the images of the distinct elements of a under f are distinct. That is, for every x1 and x2 in the domain of f, f of x1 is equal to f of x2 implies that x1 is equal to x2. Or, if f of x1 is not equal to f of x2, then x1 is not equal to x2. A 1-1 function is also known as an injective function, or simply an injection. Further, if a function is not 1-1, then it is known as many-1. For example, function f shown here is not 1-1 as 2 distinct elements, 3 and 4, of set A have the same image, -3 under f. Hence, function f is many-1. Look at functions f and g. To check the functions for injectivity, we consider any 2 different values in the domain of function f and check that their corresponding outputs are different. In the first case, different elements have different images. Therefore, the given function is 1-1. However, in the second case, the image of 9 and 23 is -4. It means that g of 9 and g of 23 is equal to -4. Hence, the function g is not 1-1. Moving forward, let's now show that the function f from R to R, defined by f of x is equal to 2x, is a 1-1 function. Let x1 and x2 be any 2 arbitrary elements from domain R of function f, such that f of x1 is equal to f of x2. Now, f of x is equal to 2x, so f of x1 is equal to f of x2 implies that 2x1 is equal to 2x2. This gives x1 is equal to x2. Hence, for any 2 arbitrary elements x1 and x2 in the domain of f, f of x1 is equal to f of x2 implies x1 is equal to x2. Therefore, function f from R to R is 1-1. This diagram shows the graph of the function f of x is equal to 2x. Given the graph of a function, you can check whether it is 1-1 or not with the help of a test known as the horizontal line test. To check the injectivity of the function f of x is equal to 2x, we draw a horizontal line such that it cuts the graph. This line cuts the graph only at one place. Such types of functions are known as one-one functions. In this graph also, the horizontal line is intersecting the graph at only one place. Hence, the function is 1-1. In cases where the line cuts the graph of a function at more than one place, the functions are not 1-1. This diagram shows the graph of a function that is not 1-1. Let's now discuss the onto function. Let's begin by considering a function f from a to b, which is shown here. From our previous knowledge, we can find the codomain and domain of the function. The codomain of function f is set B, with the elements 5, 6 and 7, and the range of the function is also the same set. It implies that the range of the function is equal to the codomain of the function. Such functions are known as onto functions. Mathematically, a function f from a set A to a set B is said to be onto if and only if for every element y of B there is an element x in A such that f of x is equal to y. This implies for every y in the codomain there exists at least one x in the domain. So we can say that the range of f is equal to the codomain of f. Hence, f is onto if and only if f of A is equal to B. The other name for an onto function is surjective function or simply surjection. The functions in which two elements are mapped to the same element are also onto, provided there exists a pre-image of every element in the codomain of f. For example, function f from A to B is onto. However, g is not an onto function since the element 4 in the codomain of g does not have any pre-image in the domain. In this module, you will learn about bijective functions. You have learned that a function f from A to B is said to be 1-1 or injective if every element of A is mapped to a unique element of B. That is, no two elements of A are mapped to the same element of B. Here function f satisfies this condition. So we can say that f is 1-1. You have also learned that a function from A to B is said to be an onto or a surjective function if every element of B has at least one pre-image in A. Here, function f satisfies this condition also, and hence it is an onto function. Thus function f from A to B is both 1-1 and onto. Such a function is also known as a bijective function or a bijection. Mathematically, a function f from A to B is a bijection if it is both 1-1 and onto. Consider a finite set X with the elements A, B and C. Let us define a function f from x to x such that it is a 1-1 mapping. Then every element of domain X has its own unique matching element in codomain X. That is, two elements from the domain of F cannot point to a unique member of codomain X.